So once again, just check if you've forgotten what the answers are. The question might ask you what is the atomic ionic radius, which is this one here. And so you might get a point for it, or it might just ask you to explain. And so you can see that there's a decrease along here. And that's because the ions here we're all going for losing electrons, and then when we start gaining electrons, it's a jump from 171 to 146, so it jumps up and then it starts decreasing. So decreasing until it hits all the cations, and then when it hits the anions it goes up a shell and then it starts decreasing across. So a lot of similarities to the atomic nuclei. And so this is a visual picture of the shells, so you can see that there aren't many electrons on the metals. That's why it's easier for them just to lose an electron to have a full shell. And the non-metals, all they need to do is gain one electron, which is much easier to do, considering trying to get some sort of electrostatic balance. It's a lot easier to gain one. There's a lot less electrostatic difference than losing 7. Okay, so the non-metals will become anions, the metals will become cations. Now, you can actually demonstrate some of this experimentally, so you can actually get so the electrons are in actual waves, and so you can actually get standing waves and can get the 1, 3, 5, 7 numbers of suborbitals. So 2 electrons in each, and so this one will contain each sort of shell here, represented here by these d orbitals, and they're called nodes in between. These are standing waves. You can actually see the shells, really, if you do standing waves to represent the electron shells. Now, the strength of these is stronger than POSNEG, which is quite rare. So first of all, they just end up having a full shell, so it's ionic covalent metallic bonding. And then there's sort of this positive attracted to negative. So this is quite strong. When they aren't, such as this atom here, we actually call it a radical and put a big dot there. That's not a free electron. That's a radical. It's sort of by itself to represent it's not in a pair, so it is quite reactive. So these oxygen radicals pretty much will react with anything. So they can cause cancer or destroy the ozone or whatever, because they just, radicals generally will just grab the first electron they can see and react with anything to have a full shell. And that's why we have all these positive negative ions. And so I've been a lot more explicit now because and underlined the really key points, just because students have trouble verbalizing it. Again, you need to sort of understand it and be able to paraphrase it yourself. So first of all, the big one is all the cations go down a shell and become smaller, the anions get larger and go up a shell. I'll let you read this for yourself. And then as we go down, it's then just a repeat of the atomic trends, that even though everything's down a shell or up a shell, we're still in a situation where as you go down, it's one shell bigger on both sides. And therefore there's the valence electrons are not drawn as closely to the nucleus because they're so far away, so less attracted. They're on an outside shell, and there's nuclear shielding as well as internal repulsion. Just be sure that you don't just say one of those minor things and grab the underlined ones, because they're the major things, all right? So first of all, they've either gone up or down a shell, and then there's an increased shell. That will sometimes get you all you need, but we don't do it that way. We are very thorough, so read those carefully. Periodic trends. This is the same as atomic nuclei. Just make sure you know the cations get smaller because they've lost electrons to have a full shell, and anions have gotten bigger because they've gained electrons to have a full shell, and it's the same deal. People often get caught on the fact that these things are all exactly the same. These ones, they have the same number of electrons, and these ones have the same number of electrons, exactly the same. Not just the same shell, but the exact same electron configuration. And so any comment about numbers of electrons is going to get you in trouble. Clearly state that the electrons are exactly not the same number in the same configuration, and it's just the nuclear charge that's increasing, therefore pulling the valence electrons closer to the nucleus, therefore decreasing in size from left to right, and then the big jump, and then again decreasing in size from left to right. And just one last point, just as a reminder again, name the actual elements and name what shells they are. Be very specific when you're giving answers.